In this video, we're going to learn about the empirical and molecular formulas and how to determine the empirical and molecular formulas for a compound or a molecule. The molecular formula for a compound or molecule is the formula which specifies the actual number of atoms of each element. So if you take a look at this picture here, there are two different substances, one on your left and one on the right. If you take a look at the one on the left, how many carbons do we have? We have 4 carbons. How about hydrogens? Count them. We have 10 hydrogens. So we say that the molecular formula for the substance on our left is C₄HO. We are literally counting the number of atoms of each element. What about the substance on the right? How many carbons do you have? How many hydrogens do you have? And how many oxygens do you have? C₂H4O2 is the molecular formula for that substance. And I know what you're thinking. How do you place them in order? Well, most of the times, the problem will actually tell you the order of the elements. Now, the empirical formula is the formula with the smallest whole number mole ratio of the elements. So, if you take a look at the substance on the left, we say that there are 4 carbons and 10 hydrogens. The ratio of the elements is 4:10. Well, can that be reduced? Yes, it can. So the empirical formula is C₂H5. The 4:10 ratio is reduced to 2:5. What about the substance on the right? The molecular formula is C₂H4O2. Well, what is the empirical formula? CH2O. Now determine the empirical formula of these molecular formulas. So again, all you're going to do is reduce the ratio. So for example, H2O2, the ratio is 2:2. Well, that can be simplified to 1:1, and so the empirical formula is HO. Go ahead and complete this list. Play the video when you're done. Did you get the following answers? Let's talk about C₂O3 real quick. For that one, the empirical formula is the same as the molecular formula because the ratio 2:3 is already simplified. So sometimes the empirical formula will be the same exact formula as the molecular formula. Now it's easy to determine the empirical formula when the molecular formula is given. All you have to do is simplify the ratio. But sometimes the percent compositions will be given. So if the percent compositions are given of each element of an unknown compound, then you can determine the empirical formula by following these steps. Percent to mass, mass to mole, divide by small, multiply till whole. These are the 4 steps that you would take in order to determine the empirical formula if the percent compositions are given. So let's take a look at the practice problems. Determine the empirical formula for a compound that consists of 88.8% copper and 11.2% oxygen. So the first step is percent to mass. So all this really is because you have a total of 100%, you are simply starting with 88.8 grams of copper and 11.2 grams of oxygen. The second step is mass to mole. So we're going to convert our mass to moles. So for copper, we are going to moles of copper. We bring down grams of copper. So that's molar mass. In 1 mole of copper, there's 63.55 grams of copper, and that is equal to 1.397 moles of copper. Now, I'm not worried about significant digits here because I'm still going through my problem and I don't want to consider significant digits until the very end. And to be honest, with these problems, we're actually not considering significant digits because at the end, we're going to be dealing with whole numbers. So we're doing the same thing for oxygen. We want moles of oxygen. We bring down grams of oxygen. In 1 mole of oxygen, there is 16 grams of oxygen. Notice that I'm not dealing with the diatomic element because this is part of a compound, and so that is the reason why we only have just one O here, one oxygen here. So we do this, divide, equals 0.7 moles of oxygen. The third step is to divide by small. So out of these two numbers, 1.397 and 0.7, which one is the smaller value? The 0.7. So I am going to divide both numbers by 0.7. And this gives me my mole ratio. 2 to 1. 2 moles of copper to 1 mole of oxygen. I'm actually going to skip the last step, multiply till whole, because these are whole numbers. The reason why that last step is there is so that we can get rid of any decimal numbers, and you'll see that in the next problem. And so now I can write my final formula, my empirical formula, Cu, there's 2 of them, and O, and there's 1 of them. So the final formula is Cu2O. How do I know that the copper comes first? You're actually going to put the elements in order by how it's listed in the problem. So you see that they state copper first and then oxygen. So in my final formula, I put down copper first and then oxygen. Let's take a look at the second problem. Determine the empirical formula for a compound that consists of 53.7 grams of iron and 46.3 grams of sulfur. Where in this case, the first step, percent to mass, it's done. They already gave me mass. I'm starting with mass. So I'm actually going to start with the second step, mass to mole. So 53.7 grams of iron. I want to convert that to moles of iron. The molar mass of iron is 55.85 grams. And that gives me 0.962 moles of iron. And then I'm going to do the same step with sulfur. Convert that to moles. So in 1 mole, there's 32.06 grams of sulfur, and that is equal to 1.444 moles of sulfur. I tend to take my numbers to the thousandths place when I'm doing the work and when I don't need to consider significant digits, because that way, the more digits I use, the more accurate the number is going to be. Next step is to divide by small. So out of these two, the smaller number is 0.962. So I have 1 mole of iron, and for sulfur, I have 1.5 moles of iron. You see how I have a decimal number, 1.5, 1.5? Well, I can't have that. I can't have half of a mole. So here I'm going to do the last step where it says multiply till whole. And so really all I do is multiply by 2 for each number. Whatever I do to one, I have to do to the other. So 1 times 2 is 2. 1.5 times 2 is 3. So my final formula is Fe2S3. Sometimes you will be asked to determine the molecular formula given the empirical formula. To do that, we're going to find N, which is the molar mass of the molecular formula divided by the molar mass of the empirical formula. And then we will distribute N to the given empirical formula. So let's take a look at the first example. Determine the molecular formula for the compound C₂HO2 that has a molar mass of 118.1 grams per mole. The first thing we want to do is find the molar mass of C₂H3O2. So go ahead and determine the molar mass of C₂H3O2. The molar mass is 59.05 grams per mole. And then the second step is to determine N. N is the molar mass of the molecular formula divided by the molar mass of the empirical. So in this case, we will put 118.1 on top, divided by 59.05. And that is equal to 2. So with that 2, we're going to distribute to every single element from our empirical formula. And so when you distribute, remember you're multiplying, our molecular formula is C₄HO4. Now when you are asked to find the molecular formula and you are solving for n, you will always be dealing with a whole number. Sometimes when you divide, you might get a value of 1.999 or 2.001, but that's close enough to round to the whole number. And so whenever you see that, just remember to round it to the whole number. An unknown molecule consists of 40% carbon and 6.7% hydrogen with a molar mass of 56.12 grams per mole. Determine the empirical formula and molecular formula for this unknown. Now you'll notice here that the percent compositions are given, so you do have to start from the very beginning using the rhyme, percent to mass, mass to mole, divide by small, multiply it to a whole. And then you're going to combine the steps that we did in the previous problem in order to determine the molecular formula. So first, let's go ahead and convert our percents to grams. So we have 40.0 grams of carbon, and I'm going to go ahead and convert that to moles right now. So 12.01 grams on the bottom, 1 mole on top. That is equal to 3.331 moles of carbon. Let's do the same thing with hydrogen, 6.7 grams of hydrogen. Convert this to moles, 1 mole on top, and we get a value of 6.634 moles. Divide by the smallest number, 3.331, divided by 3.331. We'll get 2 here and 1 here, so we have a ratio of 1 to 2. So our empirical formula is C₄. From here, we're going to now determine n, calculate n. So we're going to take the molar mass of the molecular formula that's given in the problem, so 56.12, divided by the molar mass of our empirical formula, which is 14.03. We get a value of 4. Now we're going to distribute that to our molecular formula, and so we get C₄H8 for our molecular formula. Next, let's take a look at calculating the formula of a hydrate. So remember that a hydrate means that a substance has water molecules that are bonded to the ionic compound. Just think that it's attached. It's not like a liquid substance, but it's just these crystal water molecules that's attached to this ionic compound. So after we heat a hydrate, then you are left with what we call an anhydrate. So anhydrate means without water and hydrate means with water. So let's take a look at this example. When 0.235 grams of CuCl2 hydrate, so copper 2 chloride hydrate, are heated, 0.185 grams of the copper 2 chloride anhydrate remains. What is the value of X? To determine the formula of this hydrate, you just follow these 3 steps. It's very similar to the steps of finding the empirical formula given the percent compositions. So the first step is to determine the mass of the water. So think about it. You have a substance, a hydrate that's with water. After you heat it, now you have an anhydrate that's without water. So the water evaporated. How do you determine the mass of the water? Well, you're going to subtract the mass of the anhydrate from the mass of the hydrate, right? So the mass of the water is going to be 0.235 grams minus 0.185 grams, and we get 0.05 grams of water. And then we're going to take that mass and convert it to moles of water. So to convert, we have the molar mass of water as 18.02. When you divide, you get a value of 0.005. 0.00277 moles of water. Step 2, convert the mass of the anhydrate to moles. So we're going to use 0.185 grams of the anhydrate, which is really just copper 2 chloride, and convert this to moles. So that's 134.45 grams of copper 2 chloride on the bottom of our fence. We divide and we get a value of 0.00138 moles of copper 2 chloride. So step 3, we're going to divide by the smallest number out of these two, which is 0.00138. So when we divide, we get 1 here, and we divide, we get 2 here, and that tells us that there are 2 moles of water for every 1 mole of copper 2 chloride in this copper 2 chloride hydrate. So how would we write the formula of the hydrate? This would be the formula of the copper 2 chloride hydrate.